My name is Brian Hunter. I got my doctorate degree from Rutgers University in 2014. At RDEC, we work on any caliber of munition, from small cal 50 cal 7.62s all the way up to the large artillery howitzer rounds, the 155s. Most munitions that are cartridge based in general is, I'm sure if there's any amateur rocketeers in here, they use solid propellants. So solid propellant geometries, as you can see in the figure on the right, can have very different shapes. And as a kid, you wonder why all these different shapes happen, why you have these cases where you have cross patterns, star patterns, hex patterns, anything like that. Well, that's because the shape of the grain, because of the amount of surface area that occurs as it burns, tends to affect the thrust profile because of that surface area regression. So there are three types of grains that you can come across. If you look over at number 1 in that figure, you have what's called a progressive grain, where the surface area increases as the burn occurs, and therefore your thrust profile for your munition increases. Number 2, which is a center core single perf over there, has a neutral burn. So that means your surface area and your does not change as you burn, so you get a constant thrust over time. And finally, that grain at the bottom right, number 6 down there, you actually get a regressive burn, where your thrust is high at the beginning of the burn cycle and decreases as time goes on. So the things that when we're talking about designing propellant grains that are important are the pressure seen by the grain and the actual change in surface area over time, which gets you your thrust. So typical propellant manufacturing in general are extrusion processes. They're very, very simple. Now with new emerging technologies such as additive manufacturing, we're getting more control than ever before in our design of these propellant grain shapes. You can design propellant grains with complex internal features that can tune your burn characteristics to the almost exactly what kind of thrust profile you want. The problem is that before we do testing and printing, we don't actually know what kind of a thrust profile those will generate, because the math is very hard. For simple geometries, you can do the math, you can get an idea. It's very simple to determine volume and area changes to say, okay, this is a progressive or regressive grain. As we get into more and more complicated grains, to streamline and optimize the design process, it's really necessary to have some sort of tool to be able to take an arbitrary grain shape and say, what will this do, before we go through the whole process of printing, doing burn stand testing and everything. So that's kind of where this work leads into. We've actually developed a technique through modeling and simulation using a user-based code, where what we can do is take any arbitrary CAD geometry. So you could give me this microphone, you could give me that camera, and we can put it into our software and determine how that will burn over time if you expose it to a uniform, normally surface burning or surface burn. So we validated this with many simple known shape function grain shapes, such as cord, ball grain, some simple spheres, single perf, 7 perf rods, as you can see at the top right on the left side over there. And I plotted at the bottom just the good agreement between our code for the 7 perf rod, which is fairly complicated in that it's neutral at the beginning, and then as you start getting slivering as all of those perfs start to intersect each other. The really cool thing about this, though, is we actually were able to apply this to an additively manufactured prototype grain, which our EMAP program lovingly calls the Fractal Grain, because it is a cylindrical grain made up of a bunch of cross-channel lengthwise, or a bunch of channels that basically resemble a fractal pattern. So they designed this grain with the hope that as it burned, it would continue to open up surface area and become a progressive design. So you'd have these small channels on the right, there's a large interconnected feature, and some smaller divisions that as they hopefully would open up, they would progress, have the burning surface area increase, and then allow us to have more gas generation. So after we developed this methodology, we ran it in our code, and we found from the shape function analysis that this was not true. We found that this grain actually acts very similar to, ironically, a ball grain. It's very regressive, but it has 2 progressive spikes where you get a massive spike in your surface area, but then as those channels continue to open up, they don't behave as intended. We gave this information to the program, they ran it in their interior ballistics code and found that yes, this was the case. So you can imagine that if they had gone through just using engineering intuition, designing this grain, they had printed it, they did all their stand testing, spent a lot of money doing this, they would have realized this isn't even close to what we're getting. This is almost as bad as a ball powder grain. Let's go back to the drawing board.